So we're moving on to chapter 17. And we're going to start this chapter off by looking at conjugated pi systems. So let's look at 17.1, right? So a diene is a compound that contains two double bonds. All right, we can have what's called accumulated diene, and this is where the pi bonds are adjacent. They're also called allenes. We can have a conjugated diene, okay, and this is where the pi bonds are separated by one bond. And we can also have isolated dienes. And this is where they're separated by two or more bonds, single bonds. Now, the proximity of the pi bonds is crucial to understanding the structure and the reactivity of conjugated dienes. Now, with a conjugated diene, you're going to look at the p orbitals. And in conjugated dienes, you have a continuous system of p orbitals. And as a result, the electrons are going to delocalize. I just want to make sure that you can have, so that you realize it, you can have conjugated dienes with just carbon. Let's just draw this again. Okay, here's an example of a conjugated diene, but you can also conjugate to bonds with heteroatoms. So this would be a conjugated enone. Essentially, you just have to have pi bonds that are separated by one single bond. Okay? And that describes a conjugated system. A diene is when you just have two of them. Okay, now we move on to 17.2. I'm not going to worry about the preparation. I want to look at bond lengths. Okay. So on the left here we have a conjugated diene. And the right we have a non-conjugated diene. Let's number the carbons. Okay. Now, as I said before, in a conjugated diene, you're looking at p orbitals. Now, in a conjugated system, the p orbitals, or the pi orbitals, are going to overlap, and as a result you're going to have a delocalized system. of electrons. So if we draw the p orbitals in here, okay. As you can see, when you have a conjugated system, you have overlap across the double bonds. If you look at this isolated system here, you only have overlap between 1 and 2, and then 4 and 5, which is you're going to have overlap between 1, 2, 3, and 4. What will happen is because the electrons are distributed between carbons 1, 2, 3, and 4, the single bond between 2 and 3 is shorter than a normal single bond. The reason is because it has some double bond character. And it gets its double bond character because of the overlap of the p orbitals and the electrons being distributed evenly over those 4 carbons. Now if we look at stability, okay, conjugated dienes are unusually stable. So this can be seen when we look at heats of hydrogenation. And what happens is that a conjugated diene, and I'll draw a diagram, is going to release less heat upon hydrogenation than an isolated diene. And the reason is because they contain less energy to start with. They're more stable. So if we look at the heats of hydrogenation of an isolated double bond, okay, and we're going to have to do 2 of them, plus 2 hydrogens. The heat of hydrogenation is negative 253.6 kilojoules per mole. If you look at 1,3-butadiene, and you hydrogenate it, the heat of hydrogenation is negative 236.4 kilojoules per mole. So that the conjugated diene is 17.2 kilojoules per mole more stable. We're going to explore the source of this stabilization in the next section. I want to finish up 17.3 by looking at the conformations of 1,3-butadiene. So, at room temperature, you can have free rotation around C2 and C3, so that you have an S-cis conformation and an S-trans conformation. In the S-cis conformation and the S-trans conformation, You still have a continuous P overlap. At room temperature, you have rapid conversion between the two forms. However, the S-cis is more stable, and so approximately you'll have 98% S-trans. I'm sorry, the S-trans is more stable, so you'll have 98% S-trans and 2% S-cis. Now, later on in this chapter, we'll see that the S-cis conformation is important for particular types of reactions with dienes.